Record? Oh, great. Good. So, good morning, good afternoon, good evening. It's a real pleasure to introduce the last invited speaker of ICGI, who is Guillaume Rabusseau. After a first life in musicology, Guillaume did a good move. He switched to grammatical inference. So there are still some sequences here, but not only notes. And he did a PhD thesis in Marseille. The title was beginning by a tensor perspective on weighted automata, so some relation with two-day stroke. And it was with François Denis that some of you may know, or at least this work in grammatical inference, and Hachem Kadri. Then he moved to Canada for postdoc at McGill University, and is now assistant professor at the Université de Montréal, with an artificial intelligence research chair at the Miller Research Institute. His research continues to be on the fruitful connection between tensors and machine learning for structured data. He has many publications on this area. I think it's now one of the best specialists of this field. And today we are happy, as a kind of continuation of yesterday's discussion with Gaël, he will focus on the connections between weight automata, spectral learning, and tensor networks. Guillaume, thanks for accepting this invitation, and the floor is yours.
Thank you, François, for the very nice introduction. Thank you for the organizer for inviting me. I'm very happy to be speaking here. Actually, yeah, ICGI is the first paper I got in my whole, during the end of my master. My very first paper was at ICGI in Kyoto in 2014, I think. So I'm very happy to now be an invited speaker here. Thank you for the great conference. I really enjoyed it so far. I hope you will enjoy this talk as well. And today we'll talk about tensor networks, weighted automata, and spectral learning. And so the aim of the talk is to introduce tensor networks first. And here, a quick disclaimer, tensor networks are different, though closely related to tensor neural network, right? So we heard Lee Giles and Ankur talk a lot about tensor neural network, which are this higher order recurrent neural network. And so here we talk about tensor networks, which are actually, if you talk to physicists about tensor networks, they know, a lot of them know that it's a tool that is used in to model many-body systems. When you have a lot of particles that interact with one another, it's a set of methods that allows you basically to do efficiently operation in very high dimensional, with the very high dimensional objects. So here the objects are Hamiltonian of large systems of particles, and they use this fancy tensor methods. And I will introduce this. And before being this set of techniques that is used a lot by physicists, that have been introduced like 30 years ago, tensor networks are also a graphical model to reason about tensors, which is very useful, which I discovered during my PhD thesis, and I've been advocating for it and using it everywhere as soon as I can. So then once we get familiar with tensor networks, I will talk about what the hell do they have to do with grammatical inference, right? That may not be obvious to start with. And going on in this direction, we'll talk about how this allows us to extend weighted finite automata to continuous sequences. And here we will talk a little bit about this connection with second order RNNs that Gaël mentioned yesterday. And we will talk about how tensor networks can actually help learning continuous weighted automata and scale up spectral learning in general. So we'll talk about spectral learning as well. So if you have any question at any time, feel free to either put a question mark in the chat or to write your question directly in the chat. I'm monitoring the chat here, so I can see your question. And yeah, the title of this talk could be Connecting Tensor Networks and Weighted Automata for Fun and maybe Profit, but mainly for fun. So we'll start with some preliminaries about tensor networks, weighted automata, and spectral learning, and then we will move on to this kind of three topics that I mentioned: connection with RNNs, tensor networks, and spectral learning. So most of what I will talk about today is based on joint work with my PhD student, Tianyu, who is likely here today. And this is a paper that initially we published at AIStat in 2019 about this connection between weighted automata and recurrent neural network. And now we have extended this work to include the correspondence with tensor networks. So this is most of what I will talk about is based on work with Tianyu and Doina Prakap. So let's start with tensor networks. So first, what are tensors? We all know matrices, right? We can think about a matrix as a two-dimensional array of numbers. Well, tensors are higher order generalization of that, right? So they are multi-dimensional array of numbers is one way to think about them. And for example, the third order tensor, so the three here, third refer to the number of indices or the number of modes. So a third order tensor can see it as a three-dimensional array of numbers. And so tensors are nice, but can get quite big and quite clumsy, right? So for example, a quick illustrative example of how Tensor can get quite tricky. When we want to multiply matrices with themselves, right? We know that we can take a matrix and multiply it to the left or to the right. Okay. Now, if I have a third order tensor, of course, I don't have only left and right. I have three directions. I can multiply a tensor with matrices, right, for each of the modes. And so there is this notation that is commonly used to say if I have a third order tensor T, then times 1, A will denote multiplying T along the first mode with this matrix A, and times 2 and times 3 and so on. So now if we start to formally define this, and I will just flash this little equation, you have a lot of summations everywhere and it's a mess. And when you work with tensors, a lot of the time you will get this huge lines of summation, it's awful. So this is why I will try to not show this big equation and rather talk about tensor networks, which is this graphical language that allows us to see this complex operation quite intuitively. So tensor networks are graphs, right, that represent operation between tensors. And so in tensor networks, nodes represent tensors. The arity of a node, so the number of outgoing edges, the number of legs, represent the order of the tensor. So if I have a node with one leg, it's a vector. If I have a node with two legs, it's a matrix. With three legs, it's a third order tensor, and so on. And in these graphs, so we know what vertices represent, what those edges represent. Edges represent contraction between indices. And the contraction is just a fancy word for summation, right? So for summation over joint indices. So here, if I have two matrices, A of size m by n and B of size n by p, I can connect the leg with dimension n because it has the same dimension, and it corresponds to this summation here over k, right? The summation over the corresponding index. And so this is nothing else than the matrix product, right? We see that the resulting tensor has two free legs, so two legs that are not connected to anything, m and p. So this is an m by p matrix, which simply represents the product of A and p. Okay. So we can represent a lot of common operation using this notation. For example, the inner products between two vectors, u and v, is represented like that. You see that there is, once I connected those two legs, there is no free leg, no dangling leg anymore in this graph. So this represents a scalar, a zeroth order tensor, and this is the inner product between u and v. We can then do more complex operation. For example, the inner product between tensors, which is defined similarly in this way. You connect every leg of two tensors with one another. And we can define the norm, for example, the Frobenius norm of a tensor in the same way, and so on. We can write the trace of a matrix, and of course, we can write this complex operation like this big summation. Well, it's not that big, this one, but this triple summation that we had can be concisely represented as this tensor network, where T has been, his first leg has been connected with A, his second leg with B, and his third leg with C, to get a new third order tensor, whose shape is the remaining dimension of A, B, and C. Okay. This is a very quick introduction to tensor networks. We will see them, we'll get back to them very quickly. Now, let's go on to weighted automata. So I think most of us are familiar with weighted automata, but just let's go back to the definition quickly. So we have a finite alphabet, sigma. Sigma star will the clean closure denote the set of all strings on sigma, and lambda will denote the empty string. So we all know deterministic finite automaton, right? That helps us, that allows us to compute languages, so subset of sigma star. And weighted automata, so this is a finite state machine as well, where the connection between states are equipped with a weight as well, right? So here we'll talk about weighted automata over real numbers, right? So weighted automata, you can define them over any semi-ring, but here we focus about real automaton, where the weights are real values. And in particular here, I show an example of a probabilistic automaton where all the weights are actually a positive real number and you have this probabilistic constraint. And now a weighted automata compute a function that takes a sequence and maps it to a real value, right? And in this case, to compute this value, you have to sum the weights over all paths parsing a string in this automaton. But you have another representation for weighted automata that kind of forgets a little bit or put the finite state machine aspect a little bit behind the scene, which is this operator representation, which is completely equivalent, where you can concisely represent this operation in terms of matrix and vector product. So you simply gather the initial weights and the final weights in two vectors, alpha and omega, and the other weights, you gather them in transition matrices. And so I will adopt this definition and this view of weighted automata in this talk, of course, because I want to make the connection with tensor. So this linear algebra kind of perspective is closely related to what we do with tensors, as we will see. So now formally, a weighted automata computes a function that goes from sigma star to R and is given by this set of parameters, right? So I have this initial and final weights, alpha and omega, and I have a set of transition weights, of transition matrices. So one transition matrix for each symbol in my alphabet. Right? So for each sigma in my alphabet, I have an A sigma, which is an n by n matrix. And here n is the number of states of the automata. Right? So remember before I had a two-state machine and all those matrices were 2 by 2. So really there is this correspondence between the size of these objects and the number of states of the weighted automata. And the function it computes is, if I get a sequence, sigma 1 to sigma k, how do I use this parameter to compute the value actually that the weighted automata will output? Then I just take the product of all the transition matrices associated with a symbol in my sequence, right? So A sigma 1 times A sigma 2 up to A sigma k. And this gives me a matrix, right? And so I just plug the alpha and the omega at the beginning and the end to get a scalar. Right? And this is the computation of a weighted automata. And here I've shown the tensor network representation of this, which already hints at something interesting that I stumbled upon during my thesis. And you really have this translation between the structure of the string, which is right the sequence, and this tensor network representation, which is also this line here, this chain graph that represents kind of this linear computation. We will get back a little bit to that later when I very briefly talk about weighted tree automata. Okay, so this is a weighted automata. We love weighted automata for a lot of reasons. We talked about them a little bit. They are mostly interpretable. They are very tractable. There is a lot of things that you can do with weighted automata. If I give you two weighted automata, you can easily decide whether they compute the same function. Right? Something, for example, that is not doable with RNNs. So, and among a lot of other tractable things you can do with weighted automata. And one thing that you can do with weighted automata also is that you can learn them, actually. You have a very neat algorithm, the spectral learning algorithm, which is a consistent learning algorithm, meaning that if you get data that is generated, if you have an oracle, right, that gives you data from the target weighted automata, you will be able to recover it. And the spectral learning, as Gail mentioned it yesterday, you can really see it as a weighted counterpart to L star somehow. There is the active learning part, but also this idea of constructing the table in L star is really this Hankel matrix that we will talk about in the spectral learning algorithm. So yeah, we have a weighted automata, and now the next step is the Hankel matrix. What is this Hankel matrix? Which is the equivalent of the table in the L star algorithm. So for any function, not necessarily a function computed by a weighted automata, right? So any function that goes from sigma star to R, you can define this Hankel matrix, which is a bi-infinite matrix. It's indexed by words on the alphabet, right? So you have this huge infinite matrix in both directions, where rows and columns are indexed by words. And you fill this matrix using the function f. So for example, here, for a corresponding row, AA with a prefix AA, and the corresponding column here with the suffix B, the corresponding entry will be, you will put the value of f on the concatenation of the prefix and the suffix, right? So here you get f of AAB. So you concatenated AA and B. And this Hankel matrix, there is this very, very nice result from the 70s, Carlin Pies and Fliss, that tells you that the rank of this matrix, so this matrix is infinite, right? And it's defined for any function that you have, defined on sigma star. But the rank of this matrix can still be finite, right? For example, the number of rows that are linearly independent is finite in this matrix. And this will be the case if and only if the function f that we use to build the matrix can actually be computed by a weighted automata. So to me, this is a very, very striking result that connects, somehow the fact that the function can be computed by a finite state machine to something that is very algebraic, like the rank of a matrix. And actually, the rank of this matrix is exactly the number of states of a minimal weighted automata computing f. This is a wonderful, really beautiful result from the 70s. And actually, when people looked at the machine learning more in 2000, like people like Raphaël Bailly and Su and Kakade, but mainly Raphaël Bailly more and François Denis on the grammatical inference side, they knew this theorem and they knew that the proof is constructive. And the proof is constructive. This means if you give me the matrix itself, I can actually recover the weighted automata, right? So the proof is not trivial, but it's constructive. And this is what leads to this spectral learning algorithm. So I will give a brief presentation of the spectral learning algorithm. I will not get into why it works, right? We will think of it as black magic, but it actually works. So how does that work? First, we won't deal with an infinite matrix. Of course, this is not realistic. So we will choose a subblock of this matrix. So we'll choose a set of prefixes and suffixes, P and S, subset of sigma star, and we'll try to estimate subblocks of this Hankel matrix. So we will need to estimate a couple of subblocks of the infinite Hankel matrix. First, we will have this vector HP, which for every prefix, you have the value of F on the corresponding prefix, right? So it's a vector that has the size, the number of prefixes in P. Same thing for HS is a vector that has the size of the number of suffixes, where for every suffix, you put the value of F. You estimate it or you have it from an oracle. Then we have this matrix, HPS, which is a subblock of the Hankel matrix, where for every prefix U and suffix V at the corresponding entry, you put the value of F on the concatenation of U and V. And lastly, you have the third order tensor that I call HP sigma S, where for any prefix and suffix U and V and any symbol sigma, you put the value in this third order tensor, right? So you have these three indices, you put the value of F on the concatenation of U and V, but you plug sigma in the between, this letter sigma. So once you get these four objects, the spectral learning algorithm, the kind of black magic aspect looks like this. You recover the weighted automata parameters by first doing a truncated SVD of HPS, this matrix. So you split it, you do a low rank factorization into these two parts that we will call matrix P and matrix S, rank factorization of size n, right? And n will be the size of the automaton that we will recover from this matrix, from these Hankel matrices. And then you have all this fancy linear algebra operation that basically you compute some pseudo inverses, right? So S plus and P plus here, or P dagger and S dagger denotes the pseudo inverse of P and S. And in this way, you can recover alpha, omega, your final and initial weight, and your transition tensor A. So all the transition matrices. And so A here, the tensor is the concatenation of all the transition matrices of the initial weighted automata. And so this gives rise to this efficient and consistent learning algorithm for weighted automata. It has been introduced in 2009 concurrently by Su et al. And by Yi et al. Good, so this is in a nutshell the spectral learning algorithm. So when will this work, this spectral learning algorithm? So if in the exact case, if you can compute exactly the subblock of the Hankel matrix, and if the set of prefixes and suffixes are such that the matrix subblock that you get has the same rank as the infinite matrix, so basically you took a subblock large enough to get all of the relevant information from this infinite matrix, then you will exactly recover the function f, right? Which is quite an impressive result. And you can extend that to the approximate setting. This is where you get the consistent estimator that tells you that if f is a probability distribution, you get large amount of data, like infinite amount of data. As you get more and more data, you're guaranteed to converge, like the solution returned by the spectral learning algorithm is guaranteed to converge to the true distribution. And here you can kind of have an intuitive, like if this works in the exact case, you can get an intuition about why this works also in the noisy case by a continuity argument, right? So if I have noisy estimate of all those Hankel matrices and subblocks, then as since all the operations that I do are continuous, like the pseudo inverse, the SVD, and all these things, as the noise goes to zero, then I get an estimate I get exactly the function, right? I converge to the function that I want to estimate. And for all the glory details about how to turn this intuition into actual math and sample complexity bounds, and to get the proof that this is an unbiased and consistent estimator with the sample complexity of this algorithm, I would refer, I think the best reference here, really the PhD thesis of Borja Valle, where you have all the details and did a very thorough analysis of the sample complexity of this algorithm. Good, so this is the spectral learning algorithm. One last thing that I want to talk about the spectral learning algorithm is how do we estimate those Hankel matrices, right, from data, if we are in more like machine learning setting. So let's say we want to do language modeling. So F is a probability distribution, the function that we want to learn. So here, what is our data? Our data would be a sample drawn from this distribution. For example, this S here, right? So I get eight IID samples from this unknown distribution. And I will choose a set of prefixes and suffixes, right? For example, here, lambda AB for the prefixes and AB, A, and BA for the suffixes. And I will use my sample to estimate this subblock. And so here to estimate, I just use empirical frequencies, right? For example, the first element here, I concatenate lambda and A, so I get the word A. It appears only once in this sample, so I put 1/8, right? And I go like that. So this is the easy case. Now, another very interesting setting is this algorithm, right? The spectral learning algorithm has nothing to do with F being a probability distribution. It's true for arbitrary function. So you can actually use that to learn an arbitrary function. Let's say you have a score function, you want to do regression on sequences. You can use the spectral learning algorithm as well, in theory. But you have a quick caveat here, a small caveat, is that in this setting, what is your data? Your data is a set of input-output examples, right? So for example, I have some data that tells me for the word AA, I observe the output 0.2. For the word AB, I observe the output minus 0.5, and so on. Now I want to build the Hankel matrix with that. And I have an issue here because some of the values in there, I cannot fill them. For example, the word BA, I didn't see it in my sample, right? It was not one of my input examples. So which value should I put here? I cannot put a 0, right? So we had the same problem somehow before. BA, we didn't see it, but we put 0 because if we didn't see it, we estimate its probability or the probability of this word of being 0. But in the case of regression, we cannot do that, right? It doesn't make sense to put 0. So which value to put here, it's not clear. And there's this very nice paper from Borja Vallée again with Meyer Mori in NeurIPS 2012, actually got the runner-up best paper at NeurIPS in 2012, which is called Spectral Learning of General Weighted Automata, I think. Well, what they propose to tackle this problem is to use first structured matrix completion to infer the missing entries. So for those of you who are familiar with matrix completion, it's really that the task of matrix completion is you get a matrix and you have missing entries and you want to infer those missing entries. And when the matrix is low rank, you can leverage this low rank structure to estimate those values. Right? So for example, here you can guess in this very tiny toy example, in this matrix, you know that it's of rank 2. Actually, you can show that there is a unique way to fill those 5 missing values. And so first you do matrix completion to infer those missing entries, and then you do the classical spectral learning algorithm. Okay? And here what is very important is to be able to do this matrix completion step is that the Hankel matrix is low rank. If the Hankel matrix were not low rank, you would not have any clue about how to fill those missing values. But because there is this structure, which is the low rank structure of the Hankel matrix, which actually corresponds to the weighted automata structure, so the finite state structure of the corresponding function, then you can get these values, infer them. Okay, we will get back to that a little bit later. Perfect. So now let's go to after all those preliminaries, let's go to the meat of the subject and start with the connection with weighted automata and recurrent neural network. So we talked a lot about this already. We heard a lot about this. Weighted automata are somehow robust models. So what I mean by robust is all this tractability, interpretability, a lot of nice properties that verifiability that we love. On the other side, we have recurrent neural networks that are remarkably expressive, but are like really difficult to they are less tractable, and they are we have very limited understanding about how they work, right? The inner working. And there is a lot of interesting questions to be asked between connection between weighted automata and RNN. So can RNN learn regular languages? We heard about the word of Lee Giles, or the word of Avku with Jeff Hines here. Can we extract finite state machine from RNN? We heard about all the references that Gail mentioned yesterday. Can we combine somehow finite state machine with weighted automata? And here there's also a plethora of work. I only cite a couple of them, but how to combine this neural network idea with finite state machines. It should be finite state machine with neural network, of course. And the question that we addressed in this paper with Tianu and Doina is, to which extent weighted automata are actually linear RNNs? And the subtitle of this question could actually be, like, by answering this question, we will actually answer also the question, how can we extend weighted automata to input sequences of continuous vectors? Right, because RNNs, they can take sequences of discrete inputs that we're using one-hot encoding or embeddings, but when they use embedding, for example, RNNs are machines that can compute value on sequences of vectors, continuous vectors, right? While weighted automata, initially, they are limited to discrete inputs. Okay, so let's get to that. So recurrent neural network, vanilla RNN, right? So first order RNN looks like this. They compute a hidden vector, HT, recursively by applying a nonlinear activation function G to a linear map applied to xt, the input at time t, and to the previous hidden state. And the output is computed by basically a linear transformation of this hidden state and another with the nonlinear activation function. So this is the first order RNN. And second order RNN What are they? Here we have tensor that appears. Now the update equation, so to compute your new initial state, instead of having this linear map, you have a multilinear map. Basically, you have this third order tensor W that is multiplied on the second mode by your input and on the third mode by the previous latent state. So why is it called the second order RNN? Because by doing so, you get second order interaction, multiplicative interaction between your input and your latent state. Right? Good. Yeah, so this is our second order RNN, right? And here HT is actually a nonlinear function activation applied to a bilinear map. So this map that takes xt and ht minus 1 and map it to w times xt times ht minus 1 is a bilinear map instead of a linear map that we had before. One quick side note is that, of course, like intuitively, second order RNN subsume vanilla RNN, right? So by simply adding a 1 at the end of all your inputs, right, this little trick that we use, then you can show that a second order RNN can, of course, represent first order RNN as well. So it's strictly more general. Perfect. So this is our second order RNN. If we try to look at that in terms of tensor networks, and this is not a conventional tensor network because I have this nonlinear activation function G here that I represent by this dark blue node. But so basically it looks like this, right? So you start with H0 and X1, then you multiply them with W, and you get this first H1, your first in latent state, and then you apply this nonlinear activation function. And then you repeat that as you process your sequence. Right? Actually, this looks a lot like the computation of a weighted automaton. In a weighted automaton, so remember we saw this computation here, and to make the connection more obvious, we can rewrite this in this way. So what did I do here? I defined this third order tensor that I mentioned before, where I stacked all the A sigma together. So I get a third order tensor of size n times sigma, number of letters in my alphabet, times n. And actually, if you take this vector that has all the slices, which are the A sigma, and you multiply it on the second mode by the one-hot encoding of one of these symbols, sigma, what it does is simply extract the corresponding slice. Like when you have a matrix and you multiply it with a canonical basis vector, right, a one-hot vector, it will extract the corresponding column. So it's just a way to rewrite this operation, but here the connection is really obvious, right? We have the same computation, but we don't have the nonlinear activation function. So if I remove those G from the computation of a second order RNN, I get exactly a weighted automata, right? And so this leads us to this first theorem that we had in this Aerostat paper, which tells us that weighted automata are expressively equivalent, so strictly expressively equivalent to second order linear recurrent neural network when we're talking about sequences of discrete symbols, right? So if I have a second order RNN and I have discrete symbols, I will use one-hot encoding, right, to represent my inputs. And in this case, we have a strict equivalence between the two. The number of states of the RNN is exactly the number of states of the weighted automata. But of course, RNN can compute function over discrete sequences, but also over continuous sequences, right? For example, using word embeddings. So one thing that is interesting is that once we have this view of a weighted automata, nothing prevents us to say, okay, I don't have to restrict myself to one-hot encoding, right? I could put any vectors here instead of E sigma 1, I could put arbitrary vectors. So we get this very natural definition of a weighted automata over continuous vectors. We'll simply say, continuous weighted automata is given by these three parameters, so alpha and omega, the initial and final weight, and this third order tensor of size ndn, where d is the dimension of my inputs. And how does it compute a function? So first, it's compute a function from rd star to r, so any sequence of arbitrary length of d-dimensional vector to r by this computation, right? Which is very similar than the classical weighted automata. It's just we replace those one-hot encoding by continuous vectors. And now, of course, we can ask the question, so can we learn these linear second order RNNs from data? So if we ask that for sequences of discrete symbols, this is trivial. We've shown that this is equivalent to weighted automata, so we can use the spectral learning algorithm. So of course it's possible, but the interesting question is actually, now that we have extended that to continuous weighted automata, can we actually extend the spectral learning algorithm somehow to learn a weighted automata defined over sequences of continuous vectors? And yeah, the answer is yes. So this is actually the technical contribution of our paper in Aerostat. And I will get back to how we do it really at the very end of this talk, once we've talked about the connection with tensor networks. Good. So this work was really about connecting second order RNN and weighted automata, and to extend the spectral learning algorithm to this setting, right? To continuous weighted automata. So one interesting future directions that I wanted to mention, the first one is the extension of this to tree models. So we have weighted tree automata on one side. And so weighted tree automata, what are they? Very quick glimpse at weighted tree automata. If we think about here, I just show weighted tree automata over binary trees. So I just look at binary trees whose leaves are labeled by some symbols from an alphabet. And a weighted tree automata will be given by an initial weight, alpha, a set of final weights, W sigma, one for each possible symbol that can label the leaves, and this initial transition tensor T. And it maps, right? If you think of it in terms of tensor network, it just very, very naturally maps the tree structure to the corresponding tensor networks, right? So it's really, if you look at the picture, it's really a direct translation. I use the parameters of the weighted tree automata to map that to a computation. And this is a weighted tree automata, right? You can show that this can be a formal definition of a weighted tree automata. You can extend that to ranked trees over arbitrarily ranked alphabet and things like that. So it was just a glimpse at that. And so using exactly the same idea, we could actually extend, get this continuous expansion of weighted tree automata. Right? The same thing that we did with weighted automata, we can do it with trees. And we have the same kind of equivalence between some model that exists in the neural network community, which is this recursive tensor neural network that has been proposed by Zocher et al. In 2013, I think to do sentiment analysis in their first paper, where they were doing sentiment analysis on sentences where they had access to the parse tree. Right? And so they used this kind of tree structure recurrent neural network that could leverage the parse tree of a sequence to do the classification. Yes. As a side note here, not directly related to this equivalence, but when I was thinking about this and listening to the talk, to the previous talk, we could actually use the spectral learning of weighted tree automata to extract probabilistic context-free grammar from RNNs, right? So for example, the work that was presented a couple of days ago by Barbeau et al. Here, we could be extended to a stochastic setting. We have a visibly push-down automata, right? So we can see the push and pop operation. We could learn a stochastic language from this using the spectral learning for weighted tree automata. Or we could also use this model like the recurrent neural network with ordered neurons. That was actually the base paper at ICLR in 2018, where the author proposed to a recurrent neural network model that imposed some tree structure on the neuron, basically, where they can recover parse tree from the inner working of the RNN. So it's more a side note to connect that to the extraction method that we talked a lot, we heard a lot about this week. A question that I asked myself open, I didn't really spend much time to think about it, but maybe there is something interesting here in terms of what are linear counterparts of other neural sequential models, right? For example, bidirectional RNNs, let's say you remove all of the nonlinear activation function. Do you have an equivalent in the world of formal languages? What does correspond to a model that people use in verification? Something that we're currently working on is using this idea of spectral initialization of RNN to see if we can somehow. So people often focus on extracting an weighted automata of finite state machine from an RNN, and here we're trying to do the opposite. Actually, we're trying to take a weighted automata and put it into RNN. Why? Because we want to use the spectral learning algorithm as kind of a bootstrap thing to initialize the parameters of an RNN, to potentially get a very good initialization. This way, backprop algorithm that can converge very quickly to a nice optimum by using the spectral learning as a clever, efficient method. So we'll see how that works. And this is the ongoing work of my PhD student, Maud Glizer. And so something interesting is, and this was mentioned by Ankur already previously in the conference, to try to draw a more accurate map of equivalences between weighted automata and RNNs. And here, we have, for example, this multiplicative interaction RNNs that are special case of second-order RNNs where you compress the parameters, and more generally to think about the formal hierarchy of higher-order RNNs. Try to see what are the mapping between these models and corresponding models in the formal language literature. Good. So that was about the connection here with the RNNs and weighted automata. So now let's go to tensor networks and weighted automata. And here, I will start by doing a little kind of story about how physicists could have come up with a weighted automata, basically. So in physics, there is this model that is called matrix product state, that is also known as tensor train in the machine learning and numerical analysis community. It's a way to decompose a tensor, right? So tensor can be huge, and often we want to decompose them just to reduce the number of parameters. So the tensor train decomposition or matrix product state decomposition looks like this. For example, if you have a fourth order tensor, you decompose it as a chain of third order tensors like that. And of course, you reduce the parameter, right? So initially you had D1, D2, D3 times D4 tensor, D4 parameters, and now you just have this number of parameters, right? Which is linear in the D1 in the dimensions rather than somehow exponential, right? You have the product of all these dimensions. So if the ranks are small, so the ranks are the dimension of these inner edges here, then you get a drastic reduction in terms of parameters. So for example, if the ranks are all the same, we can represent a vector of size 2 to the n with only the order of n r squared parameters, right? And this is how it is used in physics. So in physics, they use this matrix product state, for example, to find the smallest eigenvector associated to matrices of size 2 to the 50 times 2 to the 50. So you can really do crazy things. You can work with tensors, with vectors of size 2 to the 50 by you representing them in this compressed form. And what is very interesting, and I will not delve too much into the detail, but is that in this compressed format, in the MPS format, you can actually do a lot of operation tractably, like computing the inner product in time that is linear in n, for example, for vectors of size d to the n. Good. So this is the decomposition that we will talk about. And physicists actually came to machine, not all physicists, but some physicists came to machine learning with this idea, trying to translate them to machine learning. And one of the first papers maybe is the one from Miles Studenmeyer and David Schwab in 2016. Yeah, okay.
You mentioned this representation with less parameters than the original tensor. Is it possible to represent all tensors in this way, or is it only possible?
No, of course, right. So yeah, there is the trade-off by it's like a matrix. Actually, if you look at that for second-order tensor decomposition, for second-order tensor, these matrices, you get a low-rank factorization. Mm-hmm. So you can only represent low-rank matrices, but like with matrices, actually, in a lot of settings, you see that even if matrices are full rank, their effective rank is quite small. You have, and this is what we see with the Hankel matrix. Like when it's concatenated with noise, it's actually a low rank thing with a little bit of noise, and getting rid of this noise is actually useful for learning. So it's kind of the same idea here. Yeah.
Thanks.
Yeah, and R controls this trade-off between the accuracy and the number of parameters. And so, yeah, Studenmeyer and Schwab, they proposed in 2016 at NeurIPS this model to do classification. They say, okay, we will parameterize linear classification model with matrix product state in this way. So to do my classification, I will look at the sign of the inner product between some weight tensor, W, and my input X, where W is parameterized as a tensor train. So this way I can do linear classification in exponentially large spaces. So I will not get into too much details, but this idea has been revisited also by Anne et al., physicists. So here, this paper is actually in Physics Review X, where they use matrix product state to model probability distribution, to do generative modeling of images, actually. And they model the probability of X as being the inner product between X and some tensor train parameterization here. So the parameters of my model would be this G1, G2, G3, and G4. Actually, what they use is to model the probability of X, they don't use this raw value, they use the square of it. And so this has a lot of historical motivation for in the physics community. This is the Born rules that tells you that the probability is the square of the wave function, of the magnitude of the wave function. But you can also simply think of it as a nice trick to make sure that your value is positive, right? Which is something that we always have problem dealing with when we learn weighted automata, that maybe they cannot put negative values. So squaring the output, this way you're sure that you have only positive values. Okay, and so we can also use this structure to model distribution over sequences, for example, fixed length sequences, right? I can say if I want to model distribution over sequences of length 4, I can have this model with 4 core tensors, and I model the probability as that. So now, how can we model distribution over variable length sequences? And here, physicists use this thing which is called the uniform matrix product state, which is similar decomposition, but instead of having different core tensors, right? So this G1, G2, G3, and G4, you have the same core tensor everywhere. Right, and then you have you need this initial and final vectors to kind of make it a fourth order tensor. And in this case, we can model function over variable length sequences. But this is nothing else than this continuous weighted automata that we mentioned before, right? This is more a story about how this model, the continuous weighted automata, the linear second order RNN, and even weighted automata, they actually are very, very closely related to these tools, to these models that physicists have been using for decades now to model one-dimensional many-body system, quantum systems. So there is a lot of nice interaction to be made here. Good. So now we could define this uniform MPS by this tuple, and this is the continuous weighted automata that we defined previously. And so as we said, if the inputs are one-hot encoding, then this is exactly a weighted automata. If we use this trick, like the square trick that I mentioned, there is a very funny thing here that happens. So if you use this square, these Born rules from the physics to model your distribution, what you get is exactly this, for those of you who know this work from 2011, the quadratic weighted automata that was proposed by Raphael Bailly in 2011. And this is exactly the way that actually physicists use this model with the square here. So very interesting and uncanny relation here. I don't know Raphael was aware of this when he published this in 2011. In all generality, this is just linear second order RNN. And so we have this paper this year actually in AI Stats with Sandesh Srivan, Sid Srivan, Sandesh Adhikari, Jacob Miller, my postdoc, and Baron Boots that talk about all the connection between automata, this MPS model, and stochastic processes and predictive state representation and such. So in terms of future directions here, one thing that we are exploring, that my postdoc is exploring right now, is how to use sampling techniques to make very fancy sampling with weighted automata. I see I'm not running out of time, but still need some time, so we'll get I will go briefly over this future direction. Something that we are working on as well is scaling up this, the learning algorithm for uniform MPS. So for this continuous weighted automata, or even classical weighted automata, to very large state space. So using this idea of tensor train to actually compress even the inner representation of a weighted automata to try to learn huge weighted automata. Because of course, weighted automata are linear, so this limits their expressiveness. But actually, linear model, if you run them into high dimensional feature spaces, they can be very expressive, right? It's the whole story of kernel methods. And this is something that we think could be interesting, right? To combine the tractability of RNN with of weighted automata with a very large model to actually get something that is both expressive and somewhat tractable using these parameterizations. We're also investigating how we can train weighted automata, like this continuous weighted automata, with word embeddings, right? Which was some of the initial motivation for one of the initial motivation for the continuous weighted automata. Good. And so now we get to the connection with the spectral learning algorithm. And here I will give a tensor network view of the spectral learning algorithm. And so we saw here that the weighted automata and this tensor train or MPS decomposition are already intrinsically linked to one another, right? And it's not surprising that actually this connection appears in a very fundamental ways in the Hankel matrix itself, which is like the root of the spectral learning algorithm. And I will talk about that now. So we have our weighted automata. Let's focus on discrete symbols for now. Our Hankel matrix, right? So remember, we have this infinite matrix with prefixes and suffixes, and we put the value of f on the concatenation of prefixes and suffixes inside. So now let's define a new object, right? For any function, or we have let a function computed by a weighted automata. For any integer L, we will define this Lth order Hankel tensor, HL. Which is given, so it's indexed by symbols, right? By L different symbols. And very simply, the component sigma 1, sigma 2 up to sigma L of this tensor, of this Lth order tensor, is the value of f on this word of length L that I obtain with sigma 1, sigma 2 up to sigma L. Right? So this is simply a Lth order tensor that gathers the value of f on all possible words of length L. Okay. So if we go back to our definition, like our computation of a weighted automata, we can see that this value is equal to that, right? So remember, I take the product of A sigma 1, A sigma 2, A sigma k, and then I put the alpha and the omega in the between. So by looking at the equation, you see that actually this tensor H, it is an MPS tensor. It has low rank, right? Low tensor train or low matrix product state rank initially. So really, you get that this HL is a tensor, has exactly this expression of low uniform matrix product state rank, right? So what I'm getting at now is that the Hankel matrix is not only low rank, right? So this low rank property has been used and fundamental to the spectral learning algorithm, this old relation from the 70s, but we have more structure than that. You actually have that you can decompose the Hankel matrix into subblocks, right? So I take the subblocks with H2 here, the first subblock, every word of length 2, and H3 is the tensor with every word of length 3 that I reshape into a matrix of size sigma times sigma squared. And so I can decompose my matrix in there in all of this reshaping of this Hankel tensor that I mentioned. And all of these subblocks are matricization of tensors that have low tensor train rank. So this is way more than saying that this matrix is low rank. It's saying you have this kind of hierarchical structure. If you zoom in into these subblocks, it's not only low rank matrices, it's actually matricization of low rank tensors. And here the low rank structure is way stronger than matrix low rank structure. In the sense, for example, that the number of parameters is way smaller when you use tensor train parameterization than matrix rank parameterization for some tensors. So this is to me a very interesting thing that and this is where the fun is to me. This is the funny part. Then the profit part, I think there is a lot of things that can be done from that, but we are still actually currently investigating all the ramification in terms of learning that this connection can have. But so the first one is that we can use that to scale up the learning the spectral learning algorithm somehow. So in the spectral learning algorithm, remember, we need to estimate all those subblocks here, HP, HS, HPS, and HP sigma S. So if we choose P and S, the prefixes and suffixes, to be the set of words of length L for some integer L, then actually all of these subblocks are matricization of these anchor tensors. So there are actually matricization of tensors that have very low tensor train rank. And this allows us to do two things. So yeah, all the quantities that we need to estimate in this case are matricization of tensors with low uniform matrix product state rank. And so we can estimate those things directly into the MPS, the matrix product state format, right? I will talk a little bit more about it just after. But we can leverage this low rank structure a little bit like we did with the completion with matrices that I mentioned before. Here we have even more structure, which is this tensor train structure, and we can leverage it to estimate those tensors from data. And we can use the spectral learning algorithm basically we can do it efficiently. So we can do the spectral learning algorithm directly using HL, H2L, and H2L plus 1. So these three tensors that correspond to the subblock we need to estimate for the spectral learning algorithm very efficiently. And so what does the algorithm look like in this case? You get these three anchor tensors. So you estimate them from data somehow, and you get them directly into the matrix product state format. So you get the anchor tensor for all the word of length L, all the word of length 2L, and all the word of length 2L plus 1. And then you have this operation. We will not get into the details about how to do that, but basically this is doing all the spectral learning algorithm things in the tensor train format. So the important thing to see here is that the manipulation that I do, I never do a manipulation on the whole HL, which is potentially a huge tensor. I only do them on the core tensor that are involved in this decomposition. And just by doing local operation on these core tensors, I can get back my alpha, my omega, and my A tensor. So all the parameters of my weighted automata. So this is a way to do the spectral learning algorithm implicitly in this tensorized kind of compressed format. And this reduced, right? If you look at the time complexity, the time complexity of the spectral learning algorithm, assuming that these anchor tensors are given to us in the tensor train format, in the MPS format, this reduce the complexity from something that is exponential in L. So remember, L is the length of the word that I use for prefixes and suffixes. So the initial complexity of the classical spectral learning algorithm will be exponential in this length, where here we get something that is linear in L, right? Which come from this tensor train parameterization. And also, remember when I talked about learning arbitrary functions, we could use the structure matrix completion that Borja-Ballet and Meyer-Mori proposed in 2012. But actually, we can use more than the low-rank structure of a matrix here. We could actually use this tensor train structure, this matrix product state structure. And so we could fill the missing entries of the anchor matrix using tensor completion techniques instead of structure matrix completion techniques. Okay, so this is kind of the spectral learning part. And now I want to talk very briefly to conclude about the estimating those things from data, those anchor tensors. And this is to connect back to how do we actually learn from data for continuous weighted automata. So recall that in the discrete case, this HL tensor, right, is given by this, right? It's defined in the way that it's gathered the value of f on sequences sigma 1 up to sigma f. So now when I have continuous inputs, I cannot, it's not straightforward to define this anchor tensor, right? How do I index a matrix by continuous vectors? But it turns out that I can still define this HL tensor in this way, right? So if I have a function that is computed by a linear 2RNN, with parameters alpha, n, and omega, I can define HL to be this tensor, right? So I don't talk about the value of f directly, I just define these objects. And going a little bit through the math, you can see that actually, when you compute the value of f on the value, x1, the sequence of vectors, x1 up to xk, it's like plugging them into this HL tensor, and this corresponds to an inner product between this Hankel tensor, so hk here, if I have a sequence of length k, and the Kronecker product of the inputs. So why is this important? Is because actually what this thing is, the value of f on the sequence x1 to xk, it's a linear measurement of HL. And here I will not get into all the details, but this implies that we can recover this HL from input-output examples. So if you give me input-output examples, so sequences of length L, and the corresponding output y, which is the value of f on this, I don't need to observe all of them, right, on all sequences, on all possible sequences of length L. I can use compressed sensing-like techniques to estimate this HL from a few measurements, especially if the rank is small, if this n value is small. I don't need that many measurements, so that many input-output examples to actually exactly recover this HL tensor. And this is how we do it. Like, well, when I mentioned we can learn, we can extend the spectral learning algorithm to continuous weighted automata. This was the tricky part somehow. How can we estimate what is the Hankel object? How do we define it? And how can we estimate it from data? And this is the key here. It's really to see these subblocks of the Hankel matrix that has low tensor train rank that we can estimate using compressed sensing techniques. Good. So I'm reaching the end of the talk. In terms of future directions, just mentioning a couple of things. The first thing that I was thinking about again this week, and didn't think about it that much before, but all this continuous weighted automata and spectral learning thing could actually give us a way to extract weighted automata from RNNs defined over continuous inputs. So you have an RNN defined over word embeddings, and you can extract a weighted automata from it actually, using this technique. Tianyu is currently working on using this continuous weighted automata spectral learning algorithm in reinforcement learning, for partially observable Markov decision process to try if. So one thing that I want to say maybe briefly here is that right now, in terms of the implementation and how that works in practice, it's still very toyish, right? So we have this nice theoretical connection, but one thing that we are working a lot on is actually the engineering to get this algorithm work well on larger models and larger data sets so that we can get something that is of practical interest, right? So for now, it's practically interesting, but it's still limited to small data sets and small models. As I mentioned, similar connection can be derived for models on trees. We could think about connection with graphs. And overall, there is a lot of connection between quantum tensor network, probabilistic models, formal languages, machine learning to explore. And this is something that we're working in my group and very excited about. One particular direction that I want to mention is the work of Ty Bradley, who is now a postdoc at Google X, who is working, one of her work is how to use density matrices, which are at the core of quantum physics, and how to model probability distribution in quantum physics in model languages. And I think this is a very, very interesting direction, both in terms of interpretability. It can lead to a lot of, I think, interesting. So this is something I'm quite excited about. So that's all for the talk. Oh, sorry, there are a lot of information. Thank you for listening, and I'm happy to take any questions if there are any.
Okay, thank you. A very interesting talk. Many pieces of the puzzle that are fitting together, and it's nice to see these advances. Thanks a lot. Do we have questions? Raise your hand or write it in the chat.
I see Joshua had the question, I think.
Please, Joshua.
You were uploading. Okay, thanks. Thank you.
Okay. No question? Okay, I will begin, and then we see. Yeah, since the deep learning networks are successful, I'm wondering whether it's because they are using weights or whether they are using the nonlinearity. And in the grammatical inference, okay, the classical grammatical inference, we were using probabilistic model. Do you have an idea of what is the added expressivity of weights and the limitation of not having the nonlinearities?
Yeah, so I think that the limitation of not having nonlinearities is quite big. So yeah, the first thing that I would like to answer is neural network, recurrent neural network. Why are they powerful? Is because they have an efficient parameterization. It's one way to see it, right? It's the nonlinear. So the nonlinearities makes it such that you can express very complex functions with relatively small number of parameters. And when you have linear models, somehow you need way more. So you always have this idea that if you use the right feature space, like in kernel methods, right? If you expand your data in some way and embed them into a large dimensional feature space, then linear models can be very expressive, right? It's like you can express polynomial function, any continuous function can be approximated by a polynomial and so on. But you need to use a lot of parameters. So to me, this is really what makes somehow linear models less expressive is that you need way more parameters to express and complex feature space to express complex functions. And this is why I'm excited about this idea also of trying to learn weighted automata with huge stage space. And when I was mentioning this, it's really thinking about a weighted automata with 2 to the 40 states, right? If we are able to learn these kind of things, I'm really curious about whether we can get something that is actually very expressive in using the right feature space, and I believe we can, right? But then you have another issue, which is training these things. So there is a lot of tricks and that have been developed to learn to train efficiently recurrent neural network. And so training tensor networks, models like those ones come with their own bags of difficulties and numerical instabilities and a lot of things to figure out about how to train this thing in a stable manner. So this is something that, we're excited about.
And the second point about probabilities versus weights and maybe negative weights.
Yeah, so this.
Do you know some results showing the better expressivity of weights?
Oh, yeah. So you have result, right? So it's classical result from François Denis with Esposito, I think, right? Like where they show that you have a strict separation between weighted automata, like stochastic weighted automata, so weighted automata with arbitrary weights that compute a probability distribution, and probabilistic weighted automata, weighted automata with positive weights. And so you really have a separability there. You can show that there are some functions that you can only exactly, the probability distribution that you can only compute exactly with weighted automata. And you need an infinite number of states if you want to use only positive weights. And the one intuition that I have about that is that when you think about probabilistic weighted automata, you can still think about their weights, the hidden state as vector, continuous vector. So potentially, having a huge space, but you can also simply think of them as probability distribution over a finite set of states, right? So you still have this idea of a finite set of states, just you have a probabilistic treatment of these states. You model probability distribution over the states, which to me somehow seems less powerful than actually really using a continuous hidden representation, vector hidden representation. And this is kind of my intuition about why it's more powerful, because even when, to me, when you use a probabilistic weighted automata, even though you have this continuous space of states, you're still just modeling probability distribution over a finite set of discrete states.
Are there any other questions, or do I continue? Prevent. Just to continue the discussion, and because when we are speaking about the first part, about the deep learning part, the ReLU function is not really nonlinear. We can be very close from it by simply absorbing the states or values with the zeros. So that's why I don't know how much there are some difference. What is really making deep learning work and not? And maybe your approach with maybe more easy also to learn, actually, because you have less parameters in somehow.
Yeah. You have other. With respect to some aspect, it gets easier to learn, but for the other one, the optimization gets tricky because of all this multiplicative interaction. This is also so I think we need to explore also tricks that people use, like these skip connections to train very deep neural networks. Because here, this is what is happening. Like you have this A parameter that you multiply with itself a bunch of times, right? And that's always been the problem in training recurrent neural network, where squashing activation functions used to help a lot for the training and things like that to prevent this problem.
Like maybe not using exact method, stop using exact method and mathematical method.
So here, a lot of the other things that we are doing, we're actually using gradient descent and backpropagation to actually train these models, and mix between that and optimization technique that they use in physics to actually efficiently train this kind of models or optimize this kind of models.
Okay, it's very nice to discuss with you, but I would like someone else to discuss with you.
I think Alex.
Alex, please.
Oh, hi, thanks. Sorry, my video doesn't seem to be working. Thanks for a really interesting talk. So, I mean, these learning algorithms are sort of consistent. So that means they're asymptotically correct, right? But do you have anything to say about the kind of the rate at which they converge, or the sample complexity, or, you know, their kind of finite sample behavior in general? Is there anything that one can say about that? And obviously, in the worst case, we know the situation is bad, but and that's a fairly general question, I guess. I don't know if you thought about this at all.
Yeah, so we actually for the continuous weighted automata, we didn't go to the step of doing the sample complexity analysis. There are the existing result for for the classical like discrete setting, and I would expect we will get the same kind of rate of convergence in terms of the sample complexity. But here, what is tricky is that we have these two steps, right? The one that I mentioned very briefly to estimate the Hankel tensors from the data using matrix tensor completion, like matrix sensing techniques, and this is another kind of worms basically in terms of the sample complexity analysis. And actually, in this case, you don't have consistent algorithm, right? Or it's tricky to get consistent algorithm. You need a lot of conditions. But under which condition will you be able to recover exactly the tensor? In practice, it works very well. And to show the consistency, because we still show the consistency in the paper, we actually don't use the tensor completion setting, like the tensor sensing techniques. We just estimate those Hankel tensor using least square. So we don't leverage the tensor structure in the theory, and this gives us a consistent algorithm, but which is less sample efficient, right? But we cannot show that the tensor version is actually more sample efficient. Or we could show it, but it's really not straightforward, right? It's a lot of work.
I mean, does it depend on the sort of rank of the tensor decomposition in terms of the sample efficiency a lot? I mean, what's the sort of...
Yeah, it will depend on and also, so yeah, it depends exactly on that, because the rank of the tensor decomposition is the number of states of your target automaton. But also, what we saw in practice is that when you estimate those tensors from data, you should not use the true rank. So if you generate data from a target, you know the exact number of states, and you want to recover it in this synthetic experiment. When you do the rank that you choose for the tensor, for estimating the tensor, you should take it a little bit higher than the actual rank of the actual number of states of the automaton, and then truncate it afterward. But this helps stabilize kind of this tensor recovery step.
Interesting. Is that because the kind of low dimensions, then you get a sort of a noise dimension which drives out the true dimension or something like that?
Yeah. And I think it has to do with it smooths the optimization landscape, right? It's like if you use the true rank, there is basically only one place that is nice. Whereas if you use this slightly relaxed rank, right, a little bit higher, then you will get to somewhere that is not as good, because you will learn a little bit of the noise, but actually it's easier to get there. And then it's actually easier to truncate to the actual number of states that you want to recover the actual weighted automata. And this works way better. And this has to do with the fact that we don't use SVD. We use this kind of tensor optimization, because the SVD gets you the exact solution. So you're happy with that in the matrix case. But with tensors, you don't have this exact algorithm. So you need to use iterative algorithm to do this estimation. And this is closer to the gradient descent kind of story, right? It's something really that looks like gradient descent. And so, yeah, this helps smooth the optimization.
Thanks. That's great. Super interesting.
Sorry, if I could catch on to that. So you make a Hankel matrix that's greater than the known rank. I understand that. But then you say also the truncation to do greater than the known rank? Or the truncation to the exact rank?
No, the truncation to the exact rank.
Okay.
Yeah. So the idea is, basically we need to estimate this object from data, this HL. And here, in theory, this n that we use when we do this estimation should be the number of states of the target, right? If we know the number of states of the targets. But in practice, it's better to use, like n+2, n+3 to do this step, to recover this Hankel tensor, and then we will do the truncation back to n once we get that from data, just to smooth the optimization process.
Okay, no other question? Okay, thanks again, Guillaume.
Thank you very much for the
just in
question.
time.
Thank you.
Joshua, when do you want to begin?
I guess people want to have a little break at least, so let's start at 10 past, well, in my case, 10 past 3.